Bienvenidos, Ushamdi, and welcome CTS230 Section 841 students for the first 8-week term of the fall 2017 semester. This is the Networking 3 or the Scaling Networks V6 course from Cisco Networking Academy. And this morning's video tutorial and solution set is going to be on Packet Tracer Activity 9.2.2.6, where we're going to be taking a look at Multiarea OSPF. So let's go ahead and dive in here. So here's the topology we're working with. You can see that we have in the center of the screen this orangish circle here. We have area 0. That's our backbone area. And remember, when we're doing multi-area OSPF, we must have area 0. It is mandatory. Without area 0, that multi-area setup that you're looking at would not function. So in other words, if this was area 51 here, connected to area 1 and area 2, this will not work. We must have area 0 as the backbone area. And remember, we talked about John Moy's explanation as to why they came up with multi-area OSPF. And that was to provide scalability for OSPF. Because when you have everything in one huge area, you typically run into issues of convergence time because it would take so long for the link state database to converge, as well as the size of the link state database. They had to do something where they broke down the size of an area. And so that's why we ended up with multi-area OSPF. And remember his comment that really when you start doing multi-area OSPF, it becomes like distance vector. So these areas, think of the area as like a router, right? And in a distance vector configuration. Because really what we're doing between the areas is we are abstracting, we are hiding the details of area 2 from area 0 and area 1. And that's what the ABR, and we'll talk about this. I see some questions down here on the bottom. These are the area border routers, right? And so we've got these area border routers here because they reside between two areas. They have interfaces. And remember, the definition of an area border router is one interface in area 0 and at least one interface in a non-area 0 area. And so router 3 and router 1 here, they qualify as ABRs because they have their interface in area 0, but they also have an interface in a non-area 0 area, making them ABRs. And so these ABRs are going to send in a type 3 LSA, the summary LSA. And the summary LSA is simply a listing of the subnets, right? Each type 3 LSA represents a subnet that can be found down here in area 2 or likewise over here in area 1. And those type 3 LSAs, which are generated by the ABR, are flooded into area 0. And then the ABRs will then reflood them into other non-area 0 areas. So if we had a router here and this was area 51 out here, right, that type 3 LSA would come into area 0, and then we'll say this guy's connected here. And then it would come up to the ABR here, which would flood it into area 51. But all area 51 sees is a type 3 LSA that represents a subnet down here, but area 51 doesn't know that it's down here, right? Remember, area 51 only knows to come to the ABR to get to that subnet, and the ABR will get you down here. So area 51 and routers inside of area 51 have no idea of the details of area 2. All they know in area 51 is, hey, well, the ABR is telling me for traffic to go to 192.168.2.0, come to me. And that's all the routers in area 51 know, is get to the ABR. The ABR will then recurse and come down here to router 3 and get the traffic into the right area. And so what is that? That is abstraction of the topology. That is hiding of the details of these areas, right? That is distance vector behavior. And again, when we look at the area as just a router, right, that's exactly what this is. Each area is its own, think of it as its own router, it's a distance vector, because none of the other areas have all the details of any other area. They only know the details of their area. And we'll talk about those type 1 and type 2 LSAs that we're going to see. All right, so let's dive in here into this activity, but we wanted to make sure we cover that first so that we have an understanding of what multi-area is all about and why John Moy decided to do multi-area OSPF or to implement it. All right, so let's jump on to router 1 here. So we'll click in, let's give ourselves some more space. We'll jump onto the CLI, and we are going to configure OSPFv2 on router 1 with a process ID of 1. So let's go from user exec with the enable command to privilege exec into global config, and we're simply going to say router OSPF1. The first thing we'll do is we'll set our router ID to 1.1.1.1. Now, very nice activity, right? It's going to give us an easy start here into setting things up. So we're going to enable OSPF on the interface, and let's make sure we get this right, 10.1.1.0, and the wildcard mask is 000.255, and router 1 is down here, right? So you can see we've got these two networks that are sitting in area 0. I'm sorry, area 1. And so we put that first one in area 1, and then the 10.1.1.2, we're going to put in area 1 as well. So now you can see that we've got this neighbor adjacency has come up with router 9. So this cloud here, we actually can't get into this cloud. If I click on that, you can see that that's locked. So we can't get into that cloud. So we're just going to have to assume that we've got this neighbor adjacency with something over here, right? At least one router over here in area 1. If I wanted to validate that, how about do show IP OSPF neighbor? And let's stretch this out a little bit. Right, you can see that actually there's two adjacencies, one with router 9 and router 5. And so 9 is the DR on its segment, and 5 is the DR on its multi-access segment, right? So we are not the DR or the designated router. We have our dead time. Remember, that's 4 times the hello interval. By default, the hello interval is 10 seconds on multi-access and point-to-point networks, and 4 times that would be 40 seconds for the dead time. And we've got the address, right, 10.1.1.2 and 10.1.2.2, and the interface out which we have that adjacency established. So if I say do show IP interface brief, you can see gig 00 and gig 01. So that is the IP address of the neighbor, and we're up, and then here is our interface into area 0. So let's go ahead and set this up. So let's do our network command here for 192.168.10.00.0.0.3. And so what is that insider notation? Exactly, it's a /30. Dotted decimal, 255, 255, 255, 252. And so then we put our area 0, excuse me, our area 0 statement in. So a couple other commands that you can run that are listed over here. We could say do show IP protocols, right? And this gives us the information of the OSPF process that's running. And you can see here, routing for networks. In other words, what interfaces do I have the network statement configured on? We get our default distance. We see that our router ID is 1111, and it lists out number of areas in this router is 2. Remember, we have area 0 and area 1. And what types of routers are they? And the book mentions these in chapter 9. So we've got 2 normal areas, right? Area 0 and area 1. There are no stub areas, and there are no not so stubby areas. And again, those are a little outside the scope of the CCNA, but just remember that OSPF has different types of areas. You can be a stub area, you could be an NSSA or not so stubby area, right? And then the area will behave differently in terms of which LSAs are allowed to enter that area and which LSAs that area is allowed to advertise to other areas or to flood to other areas. All right, so we're going to repeat the steps for routers 2 and 3 using the same router ID. So let's get router 2 up here. And let's give ourselves some more room on router 2. And we'll go from user exec to privilege exec into global config. We'll say router OSPF1. And then we're going to say router ID 2.2.2.2. And again, no passive interface here, really not the focus. Do show IP interface brief. And so we are going to do the same thing. And let me double check. Let's see the areas here, what we have going on. All right, so we're going to go ahead and say network 192.168.10.0.0.0.3, area 0. Now this is going to bring the adjacency up with router 1. And so we'll give it a second. And did I get that right? 192.168.10.0. And that should be, there we go. Okay, it's taking a little longer. And then network 192.168.10.4, 0.0.0.3, area 0. And then we have that multi-access segment over here. So we're going to go ahead and say network 10.2.1.0, 0.0.0.255, area 0. And you can see here in the addressing table, it's giving us that information as well. And so based off of the fact that router 2 has, or every interface on router 2 is in the same area, it would be considered a backbone router, which is also an internal router, right? It meets both of those criteria. And this is probably going to bring an adjacency up with that little cloud that we see there. And there it is with router 4. So now things are going to start to get interesting, because now, let's stretch this out here a little bit. Now when I say do show IP route OSPF, we have these two OIAs, right? OSPF inter-area routes. And so if I was to say do show IP route by itself, you can see we have a legend. And the OIA is the OSPF inter-area. And it means between areas, because how are we learning about this information right here? Well, we're learning about it from the area border router, router 1. And router 1 is sending us that information, right? And it's generating those type 3 LSAs, and it's sending in that summary information so that everyone in area 0, as well as everyone eventually here in area 2, when we configure area 2, is going to know about these prefixes. So let's take a look at our OSPF database. If I were to say do show IP OSPF database, right? Here is the type 3 LSA. These are my type 3 LSAs, and take a look at them. The advertising router is 1111. The only thing I know about these is the network ID, right? If we dig a little deeper, if I were to say show IP OSPF database, oops, sorry, and I want to think it's summary, and there we go. Let's give a little more room here. So this allows me to dig a little deeper into the summary LSA. Now remember, this is the LSA, or these are the LSAs, these two LSAs here. So here is one, right? And here is the other. And we can see here are the two networks that area 1, this ABR, is flooding into area 0. And here is 10.110 and 10.120. So here are the type 3 LSAs. Let's take a look at this information in here, right? We see the link state age, and we get the link state type. It is a summary link for a network. Now remember, it's not summarization in the sense that it's going to summarize these two right? And then send in like a /23. Okay, that's not what we're talking about, right? We're talking about it's summarizing these link states by simply saying, here is the link state ID, that's the summary network number, and here's the advertising router, and there's the mask. So basically what's happening is router 1 floods into area 0, a type 3 LSA, and you'll notice we're getting it's not like a combined LSA here, right? We're getting an individual type 3 LSA for each of these networks, where router 1 says, hey, if you need to get to the 10.1.1.0/24, yeah, just come to router 1.1.1.1. Now, is this the, oops, sorry, no, let's get rid of that there with the, there we go. Is this the IP address of router 1? No, remember, this is the router ID. And again, with link state routing protocols, think of it as like the node in the graph, right? It's the router is just a node in that shortest path tree graph. And in this case, router 1 is flooding this type 3 LSA into area 0 and telling area 0, hey, anybody in area 0, if you need to get to the 10.1.1.0/24, hey, just come to router 1111. And again, it's router 1111 based on the router ID. And this is why the router ID is so critical, because in OSPF, and I hope you see this, in OSPF, it's not about routing the destination of your routing. You're not routing it to the destination network. In link state routing protocols like OSPF and IS to IS, you're routing the traffic to the node in the graph who knows about the network. And that is why the router ID is so critical, which is why when you change the router ID, and all of those exercises we did in class for the in-class labs, that's why it's so critical, is that when you change the router ID, if you're expecting that that's the router ID you're going to be using, you're going to do either the clear IP OSPF proc or the clear IPv6 OSPF proc, or as we saw Andrew figure out, the clear OSPF proc, which does it for OSPF v3 automagically, right? So again, it's all about getting the traffic to the node in the graph, which is represented by its router ID, and it will get the traffic to the destination network. And so this right here, it hides, right? This abstracts all of the details of what's going on in area 1, and this is how OSPF achieves epic scalability. Right? This is what allows OSPF to scale in a huge way, because now we're saying, yeah, we've got this ABR, and he's just going to send in this information here. Yeah, hey, to get to this network, come to me. And then area 0, as we're about to see, is going to receive that flooded information, and then ABRs in area 0 that receive that flooded information will just regenerate that type 3 LSA and send it on. But let's see what that looks like. But again, it's very, very important to understand how this achieves scalability, why it achieves scalability, and what the information is that's being sent in. And that there it is right there, right? That's it. That is your type 3 LSA. And I'm sorry, I keep clicking on the area here and I'm blowing the exercise up. So into router 3. Let's go ahead and bring router 3 online here. Let's give ourselves some more room to work with. All right, so on router 3, let's go from user exec to privilege exec into global config router OSPF1 router ID 3.3.3.3, and now we got to say do show IP interface brief, or we could refer to the address chart. I like to kind of pretend sometimes that we don't have the address chart. And so let's go ahead and say network 192.168.2.0, and that's going to be, yep, 0.0.0.255. And we need to put that into area 2. And then we're going to say 192.168.1.0. And that's also in area 2. Now we may end up with adjacencies here. I would expect that we will. Maybe it's going to take a second. And then finally, we're going to get that last interface, which is going to be the 192, what is that? 192.168.10.4. So there is router 6 and router 7. So network 192.168.10.4, 0.0.0.3, and that is going to be area 0 because this is also an area border router. And so that's going to give us that adjacency with router 2. And you can see we went from loading to full, right? You go from down to init, right, to EX start to exchange to loading to full. And so here we go. Let's now go ahead and let's say show IP route. Because what we're really interested in seeing, and what I'm really interested in seeing and talking about here, is you see these networks we've got here. So we're over on router 3. What do we see for the 10.1.1.0/24? Well, let's take a look. Oh, that's interesting. There's a type 3 OIA inter-area prefix 10.1.1.0/24. Now we know that that sits over here in area 1. What does my OSPF link state database look like? Show IP OSPF database. And you can see we keep a link state database on the ABR. The ABR is going to be maintaining a link state database for every area. So here's the summary link states for area 0. And then we've got router link states for area 2. Here are the summary link states for area 3, right? So now when we look at this, here are the type 3 LSAs in area 2. And remember, we're on the ABR, which is why we're seeing 2 sets of information. We're seeing the area 0 information here, right? Because I have an interface in area 0. And I have an interface in a non-area 0 area, making me an area border router. And so this is why the text mentions that area border routers have a little more to do than an internal router, let's say, right? Because an internal router, all of its interfaces are in a single area. But an area border router has interfaces, and again, it could be one or more non-area 0 areas. So I could have an interface in area 51, area 52, 53, 54, and area 0, and I would have to maintain a link state database for every single one of those areas. And so we're interested in area 2, right? So take a look here. Where is my 10.1.1.0? And what does that tell me? What do we see here? So there's the subnet, and look at the advertising router. It's router 3. So that's very interesting, isn't it? Because who actually advertised that routing information? Who is responsible for the 10.1.1.0 being advertised into area 0 and then into area 2? Who initiated that advertisement? Exactly. Router 1 sent the type 3 LSA into area 0, right? Whoops, sorry, I didn't want to do that. Router 1 sent that type 3 LSA into area 0. It came up here to router 2, who floods it to router 3, and 3 sort of took charge, right? 3 kind of takes over here and says, yeah, I'm now going to reflood that type 3 LSA that I learned here from area 0 into area 2. And so again, you can see that we've got an even, it's like a multi-tiered abstraction here, because now these routers over here, which I think were 6 and 7, I can't remember, but these routers here, this cloud thing, they think that, hey, if I need to get to the 10.1.1.0, I just come to router 3. And so then router 3 gets that information, and router 3 says, okay, all of these guys in area 2, they recursed to me because I am flooding in area 2 this type 3 LSA telling everybody in area 2 that if you need to get to the 10110, you don't need to know about all of this out here, right? What do they know? What is the only thing routers in area 2 know about that network right there? Yeah, the only thing they know is that to get to this network, they must come to router 3. And then the question is, okay, well, Travis, so then they get to router 3. How does router 3 know what's going on? Well, for that, we just simply scroll up a little bit further and we look here. Because remember, router 3 has an interface in area 0. So router 3, when he gets that traffic, he says, oh yeah, that network, the 10110, who told me about that? The router ID of router 1111. And then there's a final recursion where now that router 3 knows that the 10110 type 3 LSA was learned from router 1111, he looks at what? Yeah, and oh, of course, it just turns out that the router ID is also the link ID. He looks here at the type 1 LSA and says, yeah, I've got a type 1 LSA because I'm in the same area, and this is who I'm going to go to with that information. And that gives him that information, right? Because he has the information. Router 3 knows about router 1 via a type 1 LSA, because remember, those are area local scope. The type 1 and the type 2 LSA, the router LSA and the network LSA, have local area scope, which means they are only in a given area. They are not flooded into other areas like the type 3 summary LSA. And let's do one last thing here. Let's go ahead and say show Ip Ospf Database summary, right? And let's find, and there it is right out of the gate, our 10110. And look at that. It's the exact same information. Actually, that's the area 0. I wanted to get the area 2. And let's float down. So this is area 2. I'm assuming, are we area 2 here? That should be area 2. Yeah, summary link states area 2. And so here is the 10110. And look, advertising router. What is the subnet mask of that network? 10110. Exactly. It's a /24. And we know that because that is how we advertised it. And that is multi-area OSPF in a nutshell. It is simply hiding, abstracting the information from one area by sending in a summary of that information into another area. And this is what allows OSPF to scale, because you don't have to keep all of the type 1 information. If there was type 2 information, right, which is generated by the DR, and we're going to talk much, much more about the designated router and, you know, the fact that we refer to that as kind of a pseudo node, even though that's an IS to IS term, it's still used because the concept is the same, right? We're representing a multi-access broadcast multi-access segment as a pseudo node, an imaginary node that's out there in the OSPF setup. All right, so this is multi-area OSPF in a nutshell. Let's see. So the connectivity is going to be there. We're good there. And so they want us to go to router 1 here, and let's go ahead and just, for the sake of argument, we'll say in privilege exec here, ping 192.168.1.2. And that's going to work 192.168.2.2, and we're going to work there and ping 10.2.1.2, and we've got connectivity there. Now, again, we took a look at some of these commands. Let's go back though. I want to take another look here. So let's say show Ip Ospf, right? Now, these are commands that you definitely want to keep in your OSPF CCNA toolkit. Because when we look at this information, take a look at some of the information that we get here, right? We get the router ID, the OSPF process number, some other important information, right? What kind of areas, right? So we're connected to 2 areas. Now, Area 1, how many interfaces do we have in Area 1? This is critical as well, right? SPF algorithm. So how many times has the SPF algorithm executed? Which means how many times have these routers had to do that laborious task, right? That CPU intensive calculation of the SPF algorithm. And this is very key. So let's build on this activity. We get presented with these activities, and I can't stress enough, it's so much more, it's about so much more than the completion percentage of 80 out of 80, right? Let's take these activities, let's build on the conversations that we've had and pull them into the context of, here's this multi-area setup. So when we talk about multi-area OSPF, it's all about scalability, right? And remember, we talked about convergence in an area, a huge OSPF area where maybe we've got, slow, long distance links, where maybe links are going, to Alaska and then out to Siberia somewhere. And I had a student who worked for an airline company, and they had links that went from Annapolis, Maryland, out to Alaska and then to Siberia in Russia, right? So this is I'm not making this up, right? So there are companies that are out there, and they didn't need to send a whole lot of data. It was just these fractional T1s that they had. And so when you're talking about waiting for convergence to happen, or a link in Siberia, right? Let's say that land segment flaps for whatever reason. That is going to have to regenerate the type 1 LSA, and it's going to have to flood to Alaska. And maybe Alaska also goes out to Hawaii, right? So, I mean, you're talking about, and then having to come here, and then maybe to California, and then over to New York. That takes time, right? That type of convergence takes time. So another benefit, then the book did a great job discussing this, another benefit of multi-area OSPF, just like, right, we talked about EIGRP, and it was partial and bounded. There was a boundary for the updates. In other words, only the routers affected by the change needed to get the update. And that is what multi-area OSPF also gives us. It allows us to scale, absolutely, but it limits the size and scope of the fault domain, right? Because if we have a link go down here, and I'm getting ready to take that link down, the 192.168.1.0/24. If that link goes down, sure, router 3 is going to have to do a full run of the SPF calculation. And so are these guys, and I can't remember. I think this was 6 and 7. I'm not sure. But anybody in this area, everybody in area 2, is going to have to do a full SPF run. And that can take time depending on how many routers you have in the area, right? Which is why we split it up and break it up. And so let's say that this is Siberia. And let's say that this is Alaska. And let's say that this is New York, right? This could take some time, right? Undoubtedly, this could take some time. And that's why we want to bound, right? We want to limit the impact of a link flapping here over in Alaska. Okay, and it's absolutely critical. And the same thing here in New York. We want to limit it to this area. All right, so let's take a look at our questions down here. Which routers are internal routers? Remember, internal routers, all of their interfaces are in the same area, and they would all have identical link state databases. So when we look over here, the only internal router is going to be the clouds, right? These clouds here. But I don't know if they're looking for you to give the routers in the cloud. But the cloud routers are obviously internal routers. But router 2 is an internal router. Router 2 is also a backbone router. The ABRs, we clearly identified the ABRs. It's router 1 and router 3. Which routers are autonomous system routers, right? So when we look at this and we want to say, excuse me, an autonomous system router, I think they're asking for the autonomous system boundary router. And that's a router that has an interface connected to an external source of information, right? So if router 3 here had an interface and this was EIGRP, and we'll just put the D for dual, then this would be considered an autonomous system boundary router. You also hear it referred to as an autonomous system border router. So which routers are generating type 1 LSAs? Well, remember the type 1 LSA is generated by every single router. Which routers are generating type 2 LSAs? Remember, that's the network LSA. That also provides abstraction for multi-access segments. And so router 3 is going to be producing network LSAs, and so will these routers over here that it's paired with. Router 1 would be producing the type 2 LSA, so would these routers in the cloud. And the same thing here, router 2. So 1, 2, and 3 are all, 1, 2, and 3 are all generating type 2 LSAs with their neighbors out here in the cloud. Which routers are generating the type 3 LSAs? Well, that's going to be router 1 and router 3, because those are the ABRs. They're providing that summary information into the other areas. Now, which routers are generating type 4 and 5 LSAs? Remember, the type 4 and 5 LSAs, the type 4 is the summary autonomous system boundary router LSA, and that would be for information coming from an external routing protocol, right? We could redistribute as static, we could redistribute connected, we could redistribute EIGRP information into the OSPF domain, and the router doing that redistribution would then generate a type 4 and a type 5 LSA. And the type 5 LSA is that external routing information, right? Okay, how many inter-area routes does each router have? Well, to do that, we would simply have to click on the router and take a look, and we can do that by saying do show IP OSPF, do show IP route OSPF, and it's once inter-area, right? So this guy's got 2. We come over here to router 1 and we say show IP route OSPF, and this guy, he has 2, and router 2 should have 4. Show IP route OSPF. Yep, and he's got 4. So 2 on the ABRs and 4 on the internal router. That's how many inter-area routes. So why would there usually be an ASBR in this type of network? And when they say this type of network, they're simply talking about a multi-area OSPF configuration. And again, it's a use case question. There may or may not be external connectivity. You may not need that, right? But let's say that this was the internet. And so the reason that you might have an ASBR in this type of a network would be to provide internet access. So if router 2, and remember, we would want it here in router 2, or I mean in area 0, typically we'd put it in area 0, because all traffic must pass through area 0. So this way, traffic from area 1 simply comes up through the ABR and then out, right? Instead of having to go like this to get to the internet, right? It comes through area 0, the backbone area, and router 2 would probably, in most cases, have a default route. If it's a single connection here, we'd have a default route configured with that IP route quad zeros, and then we would do default information originate. And then that would get sent down to routers 1 and 3, and then they would flood that information, right? Or they would know about that information and flood that information, and that way everyone would have a default route. And so that is one possibility as to why there would usually be an ASBR in this configuration. All right, well, this is going to wrap up our conversation on Packet Tracer Activity 9.2.2.6 on Multiarea OSPF v2. All right, thanks so much for watching, and I will see you guys tomorrow night.